Mechanical mismatching. Already we have seen in statistical Gaussian model. Del P with multiply with standard deviation sigma square. AP square divided by WL, this is local. PP square D is global. AP square divided by WL, example, Dobant non-uniformity, local. Okay. This PP square D global thickness gradient. Okay. General Pelgrom law. Del of sigma of del B del P equal to AP, that is CMOS process dependent. CMOS process dependent divided by root WL, that is width length to be multiplied. After that to be take root, then it will be divided under AP. AP divided by this width length multiplication value after rooting, after after square root. Okay. Morse current mirror, example, E square del Morse current mirror sigma square del ID, sigma square del beta G square mg, sigma square del VTH, del VTH, that is variable threshold voltage, variable delta del V, variable del ID, sigma square del ID divided by ID equal to 1 by WL, AP square divided by AB by P beta square plus GMG divided by ID whole square into A square VTH. Actually here change of ID with respect to ID multiply with sigma square equal to 1 by WL multiplication multiplication from here taking one value, it means 1 by WL. Okay, then multiply with the whole, that is in AP A beta divided by beta whole square, okay, plus GMG under this how much ID, how much GMG, under this beta how much AB, then squaring, then add with the squaring GMG divided by ID, then this value multiply with A square VTH, then to be added with this, then whole value multiply with this. Here two CMOS, ID1, ID2, M1, M2, then remaining all are interconnected. Here ID equal to ID2 minus ID1, so del ID equal to ID2 minus ID1, ID equal to ID1 plus ID2 divided by 2, that is 50% after addition, then 50% of this value is ID. id1 id2 to be multiplied, add, then divide by 2. It means getting 50% value. That's all. id. Okay. Then here typically VTH mismatch is dominant. Here in x-axis log IC, here 0. Here in y-axis sigma of delta ID divided by ID. Okay, changing ID divided by ID. Here in this area weak, here moderate, here strong inversion. This is the best area efficiency. This is the best area. Here in this best area 1 by W L root to WL multiply with A beta divided by beta. This is the best area. That's why here best. Okay. 1 by WL width and length to be multiplied and then take root, then multiply with A beta divided by beta. In this beta, how much A beta? So this much, and then in this WL take 1. That one multiply with the AB. That's all. How much here coming? That much. Here in this weak signal, what will happen? What is happening here? Here 1 by root 2 WL into A VTH divided by N UT. A VTH divided by N UT. That one is not mismatch. VTH is not mismatch. Is dominant here. That's why weak here. Here is the best. So A VTH, where is the A VTH divided by NUT multiply with 1 by root L. This here also same. 1 by root L. That one is different. So here A beta is matching. This is mismatching. That's why here weak. Here best area efficiency due to A beta divided by beta. Technological mismatching. Statistical Gaussian model. Same what we have seen in the last slide. That means the same here. Analog design scalability. AP here. Here this is the local standard deviation, global thickness gradient, top and non-uniformity, general, Pelgrove law, sigma of del P, AP divided by root WL, CMOS process dependent, analog design scalability, A VTH, A threshold voltage, that is deflection layer. This is TOX root 2 into Q of NaXD to be root of Na and XD divided by COX TOX TYX capacitor acceleration. This is the deflection layer XD. Okay. So AVTH analog design scalability question mark. Is it able to scalability? Here after that root 2 also scaling here. Q Na XD divided by COX. This is TOX TYX. Here deflection layer next. Okay, here in this x-axis and in the y-axis, x-axis t-axis. Okay, t-axis. Here a, here a VTH, a VTH, m v micro a VTH. Okay, so here taking value nanometer, talks nanometer. Here taking value like this. Okay. Here VTH, IM, V micro M, A VTH equal to rule of thumb. A VTH approximately 1 m V micro M into talks nanometer. Okay. Here this is all are nanometer, 10 nanometer, 20 nanometer, 30 nanometer, 40 nanometer, 50 nanometer, 60 nanometer. Here 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. M V micro M. Okay. Here 0.12 micrometer, 0.25 micrometer, 0.18 micrometer, 0.30 micrometer, 0.35 micrometer, 0.61 micrometer, 0.7 micrometer, 1 micrometer, 0.8 micrometer. Here 1.2 micrometer, 2.5 micrometer, 2 micrometer, 2.5, 1.6 micrometer. Here this is precision area. This is the precision area. Okay. NMOS mismatching 0.8 micrometer between 0.5, 0.8 meter volt micrometer into tops nanometer. Here 0.8 mismatching NMOS leakage. This is the precision area. Okay. Thumb rule of thumb, AVTH approximately 1 m V micro M, tops n. That is nanometer. And then last, the operation amplifier and its FOMS, universal analog building block, operational voltage amplifier, op-amp. Here operational voltage amplifier, operation op-amp short. So V input P positive, V input N negative, V out, VD in equal to V in P minus V in N. It means V in P in positive, V in N, it is negative, V out, okay? VDIN. Here VCM equal to VD input V in